Okay, I hope for those students who don't attend this class, I hope I have the recording that I can post on YouTube. I tried the recording on example A and example B. For some strange reason, I don't get it yet. They usually send it to me right away, but I'll see later. At least we get this one. Yeah, that's for number 20, and then number 22. Let's do more problems. Let me ask you guys to actually select maybe 5 problems from that page 523.
Is it possible also to go over a question from 7.4 since it's like also a technique of integration?
Oh, yeah.
Like,
Yeah.
okay.
Let me know which question you want me to go over.
Number 37 from 7.4, it's on page 517.
Number 37. Number 37 from section 7.4. That is integral of x squared minus 3x plus 7 over x squared minus 4x plus 6 squared dx. Ooh, this one looks ugly. I don't know. Should I skip this?
I think this one, yeah, I was having trouble. I think a lot of people are having trouble with this one.
Okay. I guess what I think I will do first is I will make this part here becomes a completed square. Or should I? Maybe not. But this is, I believe the denominator here is not, it's not factorable, right? Okay. So let's do the partial fraction decomposition right away. That is x squared minus 3x plus 7 over x squared minus 4x plus 6 squared. That is equals to x squared minus 4x plus 6 plus x squared minus 4x plus 6 squared. But on the denominator, we will have a x plus b, and this guy here will be cx plus d. Now let's think about this. Is it okay for this pattern? The denominator is non-factorable, irreducible, and it is repeating twice. So I do the one with degree of 1, because the exponent is 2, right? So I do the one with degree of 1, and then I go up to the degree of 2. At the same time, the numerator has to be 1 degree less. So because the bottom has degree of 2, then the top has degree of 1. The bottom degree of 2 with repetition, so the top one is still degree of 1. So I need to find what are the A, B, C, and D. Multiply by the LCD. Then I will get, on the left-hand side, x squared minus 3x plus 7 equals to ax plus b times x squared minus 4x plus 6 plus cx plus d. Is it okay for this?
Yeah.
Now, when it comes to irreducible case, I strongly suggest you to use the grouping method, the first method.
I started with x. Oh, sorry.
That's okay. What do you say, Nora?
Oh no, I started with x cubed and then x squared, and then
Yeah, that's right. So, oh, you know what? You're right. Let's deal with x cubed right away then. X cubed on the left-hand side, we don't have x cubed, right? On the left-hand side, we don't have x cubed, so it is 0. But on the right-hand side, we will have only a x cubed, huh? So the a is 0. For x squared, on the left-hand side, it's 1. On the right-hand side, to get x squared, we have negative 4a. And then b, okay, right? That's the only way we can get x squared. But we know a equals to 0.
Yeah.
So because a equals to 0, then b equals to 1. Now, let's go on. How about when we look at the x? On the left-hand side, the coefficient for x is negative 3. On the right-hand side, what's the coefficient of x? The coefficient for x on the right-hand side is 6a. And then negative 4b. And then plus c. Is it right?
Yeah.
Okay, now then we know the a is 0 and the b is 1. So I get negative 3 equals to negative 4 plus c, therefore c equals to 1. Now, that's not too bad, huh? Finally, the constant part. On the left-hand side, we get 7. On the right-hand side, we have 6b plus constant d. But again, because b is equal to 1, so we get 7 equals to 6 plus d. D is equals to 1. Now, therefore, our x squared minus 3x plus 7 over x squared minus 4x plus 6 squared is equal to 1 over x squared minus 4x plus 6, and then plus x plus 1 over x squared minus 4x plus 6 quantity squared. At least we are done with the partial fraction decomposition. Then how to integrate this? To go back to the integration, then integral of x squared minus 3x plus 7 over x squared minus 4x plus 6 quantity squared dx. That's equals to integral 1 over x squared minus 4x plus 6 dx. I do divide at impera. I will split them and then conquer them one by one. The first integral, then I do completing the square. This is x minus 2 squared. What's the leftover? Plus 1 or minus 1?
I got plus 2.
Plus 2, that's right. Okay, plus, I will take care of this later on. Okay, let's do that one first. I will go back there. The good thing with me, I have eraser. I can just erase that, right? I have a big eraser here. Okay, then this will be integral of, if you do u substitution, u equals to x minus 2. So du equals to dx, right? So that will be 1 over u squared plus 2 dx. Don't forget the plus blah 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 that I need to continue later on. This is equals to, if anybody remember?
1 over radical 2 inverse tangent of x minus 2 over radical 2.
Let me do it this way first. U over radical 2 for now.
Oh, okay.
Okay, and then I substitute that u back 1 over, I need to rationalize the denominator. So this will be tangent inverse of x minus 2 over radical 2 plus that integral. Okay, at least we are done with 1. Okay, I don't write the plus constant because I still have another integration to do. Let me look at here. So what happened on the second integral? Oh, this is ugly. This is x plus 1 over x minus 2 squared plus 2 quantity squared dx. Any idea how to attack this?
I used the same u, and then I got u plus 2 is equal to x, and then x plus 1 is u plus 3.
That's right. I have that in mind too. So I get u squared plus 3. I'm sorry, this should be 2 here. Squared, and this is du. Now, what next?
And then I split it up
That's true.
and did
Can you
u
tell-
over that.
Can you tell us what's the reason you split it up? That's how we actually learn, right? What's the reason you split it?
Yeah. I split it just because I could find the integral of a u over u squared plus 2 squared, because if you take that u squared plus 2 and make it into another substitution, if you take another variable,
Yes.
so like t is equal to u squared plus 2,
That's
then it's
right,
just the
So-
derivative of u squared plus 2 is 2u.
Okay. So later on, our issue will be actually on the last term,
Yeah.
last integral, right? So this is plus, let me insert something here. Let me use w equals to u squared plus 2. So dw will be 2u du, such that this is integral, 1/2 integral of w to the power of negative 2 dw, right? Plus whatever that thing is. Is it okay? Then I continue. Let me shift a little bit to the left so that I have enough space.
Mm-hmm.
I copy the first term. And then when I integrate the second term, I think I get negative. Get negative 1 over 2w. Am I right?
Yeah. Yeah.
Okay, and I will worry about this later. So this should be du here. This should be du. Okay. square root of 2 over 2. Tangent inverse of x minus 2 over square root of 2 minus 1 over twice the w, which is what? That's my w. U squared
U
plus 2.
squared plus 2.
So this is u squared becomes plus 4. I distribute it right away. Okay. Plus. What is my u again? It's u minus 2, huh? What? I do it later. Okay, now then let's start taking care of the last term here. Any idea what we should do? The key is here.
This is where I got stuck.
Okay, I don't know what to do first, but I don't know what to do either. But I think what I will do is the following. I will use trig substitution. U equals to square root of 2 tangent theta. So du is square root of 2 secant squared theta d theta. Is it okay? Now therefore u squared plus 2 will become 2 secant squared theta, right? And u squared plus 2 being squared will become 4 secant to the 4th theta. Is it right?
Yeah, so why not use tangent in this case? Oh, sorry. No, never mind. You did. I'm sorry.
Yeah, that's what I use. Okay, so I skip a little step here and there. The 3 go out, the 4 also go out. And then on the du, I get radical 2 secant squared theta d theta. While at the bottom, I have secant to the 4th theta d theta. Simplify that a bit further. Let me shift that even further to the left. This is actually 2x squared. What's that again? Because my u is this. U squared plus 2 will be my u squared plus 2. My u squared plus 2 is actually x squared minus 4x plus 6. So if I put it back there, it will be minus 8x plus 12 plus 3, 4, 3 radical 2 over 4 integral. Now, try to simplify this thing here. Secant squared on the top, secant to the 4th at the bottom. I have too many d theta. I need to erase this. Now, if you simplify that secant squared on the top, secant to the 4th at the bottom, what do you get?
Okay. Cosine squared theta, or 1 over secant squared theta.
Yeah, let's use 1 over secant squared. I will use cosine squared. And then from there, we will use half angle or double angle, right?
Yeah.
Okay. Let me copy paste this. I'm quite lazy. Let me lasso that. Okay. Copy. Paste. Lazy guy. And then integral, this will be 1 plus cosine 2 theta over 2 d theta. parentheses theta plus 1/2 sine 2 theta plus constant. Is it right?
Mm-hmm.
This is now becomes 8. Now I need to look back what's my theta do. My tangent theta is u over radical 2. Oh, this is a long question, huh?
Very.
If this is theta, this is u, this is radical 2. So this is u squared plus 2 under square root. Then, so theta will be the tangent inverse of u over square root of 2 plus 1/2 sine 2 theta. Sine 2 theta will be 2 times sine theta cosine theta. This is 8. That's tangent inverse. What's my u again?
X minus 2.
X minus 2. Okay, plus the 1/2 times 2 cancels. What is sine theta? Sine theta will be u over that times radical 2 over that. So I get I'm pretty much done, huh? Just be aware. I will not go on. I will not go on. I will just stop here, but you should go on yourself. Notice that this term here can be combined with this term. This term. Yeah, don't forget to distribute that first though. You see what I mean? Okay, and then later on, our u here, don't forget to replace that by, what's that, x minus 2? Simplify that a little bit further. Okay, and you just use the dot dot here. Okay, I think that's how I will end it for that question. How is everybody?
Hello.
Okay. Thank you.
You're very welcome. Hey, this is the type of question I would like you to ask me. You know, because sometimes I myself, I expect you too, when you see a problem that you don't recognize at all, you tend to be stuck, right? Okay, and it's really looking back and see what we have learned, you know. What makes this question a lot harder? First, you need to do partial fraction decomposition. After we're done with partial fraction decomposition, which happens to be type number 4, right? A more complicated one. So by the time you find the partial fraction decomposition, there is a big chance you are already tired. Agree? Yeah, because you get used to short questions, right? But no, once you're done with partial fraction decomposition, it turns out that's only 1/3 or even 1/4 of the whole work. Now, the first term of that partial fraction decomposition requires us to do completing the square and memorizing tangent inverse formula. Okay, the integral for that gives us tangent inverse. The second term, on the other hand, requires us to be able to see, you know what, I have something x squared here, right? And on the top I have x, so I can do substitution. right? But when I do substitution, I have leftover. This 3 as the leftover that I need to take care separately. You see? And as you can see that we actually spend more time on the last term, right? Notice that this question requires us to know partial fraction decomposition, inverse tangent formula, and then trig substitution, what else? And the regular substitution. It's a very rich question, I know. Thomas, will you ask this type of question in my test? Not sure though. Here's the thing. I have seen many times that I actually ask students to do it in an easy way, but they found out a difficult way to do it. You know, and of course, so if you ask me, will I ever ask you that kind of question? My answer is like, no, not in my test. Maybe in your take-home quiz, like if I give it as a project, then yes, possible, right? But in my test, no, but some students still find a way to do it hard way. Now, that one, I don't know how to help. Okay, try to think simple. Okay, other question besides this? Let's go back to 7.5. More questions from 7.5 maybe? Number 34 from?
7.5.
7.5. Okay, let's see. Number 34 from section 7.5. It's integral from pi over 4 to pi over 2 of 1 plus 4 cotangent x equal over 4 minus cotangent x dx. Ooh, I honestly, my reaction is almost always, I don't know what to do.
That's me all the time.
Yeah, because we need to pause a little bit, step back and see, you know what, is there anything I can simplify maybe? Right? Let's see. I think what I will do is, I'm a bit scared with the cotangent thingy, you know. So let me make it cosine over sine.
Okay.
That's not cotangent to the x power, is it? It's just regular cotangent x.
It's just
Just-
cotangent.
Yeah, just cotangent x. So if I multiply by sine x for each term, I honestly don't know where we are going though from here. Sine x plus 4 cosine x equal over 4 sine x minus cosine x. Well, what to do from? Let's try to multiply by the conjugate. Let's try to multiply by the conjugate. So multiply by the conjugate is for the denominator 4 sine x plus cosine x on the top also. The purpose is so that on the denominator we get 16 sine squared x minus cosine squared x, while on the top I will get 4 sine squared x and plus 17 sine x cosine x plus 4 cosine squared x. Now, 4 sine squared x plus 4 cosine squared x give us what? That will give us 4, right? And this will be 17 sine x cosine x. While on the denominator, notice that cosine x is actually 1 minus sine squared x. So I can write this as 17 sine squared x minus 1.
17 or 16?
Huh?
16? 16 sine squared x minus 1 or 17?
17, because from that cosine squared x, we have extra 1, extra sine x.
Okay.
Right.
But that negative, the negative cosine doesn't like subtract it. It just
It's that will be, let me use another color. So that will be minus 1 minus sine squared x.
oh okay.
Right?
Yeah.
Okay, so negative and negative give us another sine squared.
Yeah.
So hopefully we go closer to what we need. Honestly, I still don't have any clue what to here though. I don't know what to do from here. I know I can split and get something on the second term. So 4 over 17 sine squared x minus 1 dx. That one I don't know what to do. And the one here, however, I can do u sub.
You can't factor out 1 over 17, can you?
On which one?
Oh, no, you can't because it's not part of a factor. Never mind.
Yeah, it's we still have that minus 1, huh? For the second part, I can use u equals to 17 sine squared x minus 1. So my du becomes 17 times 2 sine x cosine x. Yeah. You see what I mean?
Wait, going back to like when we multiplied the denominator, like at the top where we did 4 sine x, was it plus or minus? Wouldn't it be minus 4 sine x? Because isn't it the denominator 4 sine x minus cosine x? We added it.
Which one are you talking about? The denominator
So
here? Here?
yeah, okay. So you did like you added it. So aren't you supposed to multiply it by 4 sine x minus cosine x? Because that's the denominator, but we added it.
I still don't see what you mean.
Okay.
I multiply by the conjugate.
Okay, the conjugate. Okay.
Yeah, so I get difference of squares.
Okay.
Right?
Would it be like different if we could have multiplied it by the denominator, just the negative instead of the positive? Well, the addition. So like instead of doing 4 sine x minus cosine to the top and the bottom. Instead of instead of doing the conjugate.
Ah, you know what? We are working super hard, huh?
I was gonna say because it would have been
Oh man, it hurts me so much. Thank you,
yeah.
thank you, thank you.
And I was like, why are we like all the way in the 17s? And stuff?
Yeah, you know what? Sorry, everybody. Sorry. I'm thinking way too hard.
No, it's okay. I just wanted to make sure like
No. Well. Anyway, I don't like what I did here because it seems to be way too long. Anyway,
yeah.
I kind of like focus too much. See, that's what happened. If I get scared with the problem, I cannot really pause and see what kind of trick actually happens there.
Yeah.
Let me erase this. I'm doing this way too hard. Thank you.
You're welcome.
Let me last one. Okay, so let's look back. So I have this is equals to integral. Notice that, okay, let me substitute this first. This is sine x plus 4 cosine x over 4 sine x minus cosine x dx. Everybody okay with this?
Yeah.
Now, what I didn't notice that is this. That if this is my u, if this were my u, what is my du? It'll be 4 cosine x
Plus cosine x plus sine x.
plus sine x dx, right?
Yeah.
But that's basically what I have on the top. Do you see that?
Mm-hmm.
What the fraction? So if I look back here, so okay, let u be 4 sine x minus cosine x. So du will be 4 cosine x plus sine x dx. And u of pi over 4 will be 4 times sine pi over 4 is radical 2 minus cosine pi over 4 is radical 2. That's 3 radical 2 over 2. While for u pi over 2, that will be 4 minus 0. So now my integral becomes integral from 3 radical 2 over 2 up to 4 and du over u. See how nice it is? Which is natural log of u plus constant. No, this I don't need plus constant because it's definite integral. So from 3 radical 2 over 2 up to 4. So this is natural log of, when I plug in, let's what am I doing? Natural log of 4 minus natural log of 3 radical 4. But we can simplify this further, right? This is natural log of 8 over 3 radical. That's natural log of 4 radical 2 over 3. What question is this again? Number 34?
It's 34, yeah.
Yeah, anybody have the solution?
Isn't it ln parentheses 4 square root 2 over 3?
Yeah, that's what I have here.
Okay, yeah, that's what I got.
Mhm. Yeah, I didn't really pay attention to, man. Yeah, I didn't really pay attention to this though. Yeah, let's mark this here. So you see that on the denominator, if I add that becomes my u, the numerator happens to be the derivative. And that actually helps a lot. So this is the derivative of this u here. Okay, it becomes very, very nice. Okay, thank you. That's a big help. If you didn't stop me earlier, I would just keep on going doing those silly things.
I figured it was going to take like forever to finish it.
Mhm. Okay, let's see something else. Any else?
Hey, Professor, could you scroll back up for just a second?
Sure.
Actually, can you scroll all the way up? Okay, stop right there. Okay, step there that I had to look at again. Okay, I'm good. Thank you.
Okay. Now tell me other questions. While waiting, let me show you how to do number 30. Number 30 is actually on the easy side, but we need to be disciplined with notation. This is integral from -1 to 2 of absolute of e to the x minus 1 dx. Now, the thing is, e to the x minus 1, e to the x itself looks like this. This is e to the x. So e to the x minus 1, we'll drop that down by 1 unit, like approximately like this. Now, the domain of integration will be from -1, from -1 up to -1 up to 2. Now, what you need to be aware is that in some section is on the negative side, the other section is on the positive side. So I need to break this integral up. It becomes integral from -1 to 0 of absolute e to the x minus 1 dx plus integral from 0 to 2 of absolute of e to the x minus 1 dx. Now, between -1 to 0, the expression e to the x minus 1 is negative. So when I get rid of the absolute sign, I need to pull the negative of that e to the x minus 1 dx. While between 0 to 2, the graph is already above the x-axis. So we are safe to get rid of the absolute sign. Now, basically what I did there is coming from the following property. E to the x minus 1 is equal to e to the x minus 1 for x greater or equals to 0, equals to the negative of e to the x minus 1 when x is less than 0. I wonder if you remember this from pre-calculus.
No.
No?
Yeah. No.
Okay. Now, in pre-calculus, we learn it this way. In pre-calculus, we learn it this way. So let me use a little space here. In pre-calculus, we actually learn it this way. Absolute of x is equals to x when x is positive or 0.
Mm-hmm. Right.
Okay? And equals to the opposite when x is negative. Now, in other words, if the guy inside the absolute sign is negative, and we want to get rid of the absolute value, we need to apply negative sign.
Right.
Now, that's what happened here, because e to the x minus 1 may be positive, may be negative. Now, when it is positive, e to the x minus 1, when it is positive, which can just take off the absolute sign, while if the absolute of e to the x minus 1 itself is negative, when I take away the absolute sign, I need to apply the negative. Okay, so that's how we're supposed to do it. We can modify this question to a bit simpler question so that you can see what I was actually trying to do there. Imagine if instead I want to integrate this integral from negative 2 to 4 of absolute x minus 1 dx.
Oh God, where did it go?
Now, integral from negative 2 to 1 of absolute x minus 1 dx plus integral from 1 to 4 of absolute x minus 1 dx. Now then from here, in this interval, x minus 1, let me draw x minus 1, this is the graph of x minus 1. This is the graph of x minus 1. Now between negative 2 to 1, it is below x-axis, right? Okay, so when I replace this absolute of x minus 1 without absolute sign, I need to put negative of x minus 1 dx. While between 1 to 4, the graph of x minus 1 is above x-axis. So I can take away the absolute sign for free because the guy inside the absolute sign is already positive.
Mm-hmm. So it's just regular x minus 1. All right.
That's correct. That's correct. So if the guy inside the absolute sign is already positive, we can just take off the absolute sign. If the guy inside the absolute sign is negative in that interval, then I need to apply negative sign to make it positive. Okay, now that's the idea of the problem I actually did earlier. But what we did earlier was with e to the x. Okay, it's with e to the x. This part is supposed to be on the easy side, but require us to know how to integrate absolute value, and how to integrate absolute value basically to separate the interval where it is positive and where it is negative. Now let's do one more problem before we take a break. Okay, since I don't hear anything from you, I will just do pick problems. Number 44. Integral of square root of 1 plus e to the x dx. Any idea? Don't think too hard. I think I will do u equals to 1 plus e to the x. So du will be e to the x dx. So du over e to the x equals to dx. But when we do substitution, once the variable of integration is u, then we cannot have x anymore. Okay, so I have to go further and say dx equals to du over what?
EU?
Almost right. U minus 1. Okay, now then I put it back. This is equal to integral u to the power of 1 half du over u minus 1. Now then, how to do it from here? Any idea?
Then you're going to have u. Wait, hold on. Shoot.
I'm down. I'm down. I'm not. I want to look back.
Trust me, I myself don't know what to do. But let's see. I
Can-
would like.
Is it
Yes.
possible to subtract the u 1/2 with the u, or
The thing is, we have two terms on the denominator instead. If this is only
okay.
one term, then yes, we can, but not in this case. Let's see.
And trying something with like a trig substitution wouldn't help, I guess, because it's.
Let me do this substitution first. Let's say y equals to u to the power of 1 half. So y squared equals to u. So 2y dy equals to du. Therefore, then I get integral of y over y squared minus 1, and my du becomes 2y dy. What do you think? So this now becomes integral. I can take the 2 out, y squared on the top, and then this is y squared minus 1 dy. It seems to be too nice to be true though.
Yeah, okay, that's it. And then, okay. And then you can make the y over 2 into a 1, right? Or no?
Y over 2 into...
No. Sorry, forget it. I don't know what I'm saying.
From here then, well, honestly, from here it's actually quite easy. So this is 2 times integral y squared minus 1 plus 1 over y squared minus 1 dy. Let me put it here. So this is 2 times integral. The reason I did that because, well, this is actually proper fractions, right? These have the same degree, so we're supposed to subtract to divide. Now, but when we divide, we will get this and that. You see how I played it? So the yellow one now becomes 1 plus 1 over y squared minus 1 dy. You see that? So this is 2 times y plus integral of 1 over y plus 1 y minus 1 dy. I wonder if you remember how to integrate that. We have a formula for that. 1 over 1 minus negative 1 ln y minus 1 over y plus 1. Take a look in one of your notes. And actually, you can simplify further from here. Imagine if I multiply the top and the bottom by the conjugate. If I multiply the top and the bottom by the conjugate, at the bottom I will get 1 plus e to the x minus 1, while on the top I will get square root of 1 plus e to the x minus 1 squared. Let's see. And that is 2 ln square root of 1 plus e to the x minus 1, while at the bottom there will be minus x. Let's see. This guy here, minus ln of e to the x, right? Ln of e to the x is equal to x. Okay? Oops. I think if you happen to see the substitution, I did it because I just let it flow. But if you happen to see a better substitution, number 44, integral of square root of 1 plus e x dx. If I use y equals to square root of 1 plus e to the x. So y squared equals to 1 plus e to the x, 2y dy. I do implicit differentiation equals to e to the x dx. And go on further, then 2y dy over e to the x equals to dx, but e to the x is y squared minus 1. So this integral suddenly becomes integral of y times 2y dy over y squared minus 1, which is integral of 2y squared over y squared minus 1 dy, as what we have up there. Now here I did the two-step substitution. If you happen to see that at the bottom here, I combined those two substitutions into one. But again, if you ask me to do this problem in a test, I tend to do it with the top method, because I don't know what's the result though. You know what I mean? Okay, let's take a break right now. It's 5:42. Let's take a break. We come back at 5:55.
Could you scroll all the way down, please?
Yeah, sure.
Thank you.
Here? Or even further?
Further, please.
Here?
The end of your, yeah, right there.
Be back at 5:55. Other questions beside this? Suggest some more questions.
Maybe 31.
Number 31. Oh, that looks ugly. But I think I will work with the conjugate. In a second. Number 31. Integral of square root of x plus 1 plus x over 1 minus x dx. I will see this as square root of 1 minus 1 plus x over square root of 1 minus x dx. What do you think we should do? I think I will multiply, let's do the side. So square root of 1 minus x, 1 plus x over square root of 1 minus x. You see, imagine if I would like to have square root of 1 minus x squared. Then I will need to multiply by square root of 1 plus x. Is it right?
Could you use trig substitution?
Hmm?
Could you use trig substitution?
Then after that, I will use trig substitution. So then when I multiply by the conjugate of the denominator, then I get a 1 plus x on the top over square root of 1 minus x squared dx. You know what? I can split this. This
Yeah,
is
split it, one over-
one
one
over
over x.
first, 1 over 1. This thing dx plus integral of x over square root of 1 minus x squared dx. What is the integral of the first term?
Sine inverse.
That's correct. That's sine inverse x. And how about the second one? Then we do u substitution, right? U equals to 1 minus x squared du equals to 2x dx. So then this becomes negative 1/2 integral of du over u to the power of 1/2. I think you can integrate it from there yourself, right? Okay, any else? Let's take a look on number 42. Integral of tangent inverse of x over x squared dx. I don't know how to integrate tangent inverse x, but I know the derivative. So very likely this has something to do with integration by parts. So let's see. Let's say my u be tangent inverse x, and my dv be x to the negative 2 dx. The derivative of tangent inverse x is 1 over 1 plus x squared dx, while the integral of x to the negative 2 is negative 1 over x. So this integral becomes uv negative tangent inverse x over x minus integral of v du. Over x times x squared plus 1 dx. Wow, and how to do this? At least I'm done with the first term, right? I'm sorry, I'm missing over x here.
What about partial fraction decomposition?
That's
the
right,
second
that's
part?
where we are going to.
Oh.
Mhm.
Oh, okay.
No, actually, no other way, right? If you think about it, x times x squared plus 1, that's equals to a over x plus something x squared, something over x squared plus 1. So this has to be bx plus c. Multiplied by the LCD will give us 1 equals to a times x squared plus 1 plus bx squared plus cx. Let me distribute the x right away. Then from here, I see for x squared term, on the left hand side is 0, the right hand side is a plus b. For the x term, it's on the left hand side is 0, on the right hand side is c only, right? But the constant term on the left hand side is 1, on the right hand side is a. Okay, so a equals to 1, therefore the b is negative 1. So that 1 over x times x squared plus 1 now equals to 1 over x plus, actually minus, minus x over x squared plus 1. And b, what's my b? My b is 1. My b is negative 1, my c is 0. Okay, so continue from that integral, and the integral is negative tangent inverse x over x. That's the original question. plus integral of plus integral of 1 over x dx minus integral of x over x squared plus 1 dx. I think you can go on yourself from here, right? Use u equals x squared plus 1. Okay, now of course don't forget at the end this constant. I did number 42, number 44, number 31, number 30. Now I'm lost. You tell me what you want me to do. Let me try number 50, integral of 1 over x squared square root of 4x plus 1 dx. Any plan?
Do we multiply by the radical?
That's actually one way.
Use substitution.
That's another way. I think I will use u sub, but I don't know what substitution should I use. Any idea?
Or I think the 4x minus 1?
Yeah.
For x plus 1.
Yeah.
Oh yeah, plus 1, yeah.
So this is for the x. Okay, so what happened to our x? So that will be u minus 1 over 4 quantity. That's for our x, right? So that integral becomes our dx becomes du over 4. And then I get 2 to the power of 1 half here. And here I have u minus 1 squared over 16. Let me clean it up a little bit. Together with that 4, I get 4 outside. And then 1 over 2 minus 1 squared u of 1 half d. And then I think we'll do the following. Let me say that w equals to u to the power of 1 half. So w squared equals to u. 2w dw is du. Then I get 4 times.
You mean
I'm
to
sorry,
write
this is,
du?
yeah, that should be du. I say du, but I wrote dw, sorry. That should be du. So my du is 2w dw. And then at the bottom, I will get w squared minus 1 times w. Oh, the w cancels. So I get 8 times integral dw over w squared minus 1. Do you think we can go on from here? This is 4 times natural log of square root of 4x plus 1 minus 1 over square root of 4x plus 1 plus 1 plus constant. Now I will multiply the top and the bottom by the conjugate of the denominator. So I will get square root of 4x plus 1 minus 1 squared on the top. And at the bottom I will get 4x plus 1 minus 1. That will give us 4 times ln of square root of 4x plus 1 minus 1 squared over 4x. So let me fast forward. This will be 8 natural log of square root of 4x plus 1 minus 1 minus 4 times natural log of 4x plus c. But I think if you look at the solution manual, I'm not sure though, I don't know. But if you look at the solution manual, you will see that they only write as ln x instead of ln 4x. Now, of course, we need some reason. The reason is because that's 4 ln 4x is 4 ln 4 minus 4 ln x plus constant, right? Now then, this is actually a constant. combined together with that constant give you another constant. So let me fix it. So this is 8 ln square root of 4x plus 1 minus 1. Finally, we will get this answer. Plus a new constant. Yeah, because those negative 4 ln 4 combined with the original constant, now we have a new constant. Okay. Now the way I did it here, I use substitution. Somebody said something earlier besides using substitution. Hello.
Yeah, I said that.
Somebody say something else besides using substitution.
Oh, yeah. I think that was.
I said about multiplying the radical out. That's what.
Multiplying the radical out from where?
From the beginning, from the radical 4x plus 1 at the beginning. That's what I said, but maybe that's not what you were asking or trying to refer about.
Well, we honestly never know. We never know. So let's see this problem again. I don't want to say that it's wrong until I know that we get stuck. So you say that we multiply square root of 4x plus 1 out.
Oh, yeah.
I don't see it's doable though. I mean, we definitely cannot bring this out from the integration like suddenly it pops up outside like that. No,
Yeah.
there's no way, right?
Yeah, no, yeah. Because I was just trying to think like outside of the box, because sometimes some of these questions seem to be a little too, like they look easy or they look like similar to how an easy process would be, but it's actually an alternative.
Yeah. So, but keep in mind the way we do a problem may be more than just this one method. Okay. So that's why I don't want to say that your method was wrong until I clarify that what you meant was bringing the square root outside the radical. Then we cannot do that because inside that, under that radical, we still have a variable x. You see? So therefore, we cannot pull it out from the integral. No. Now, let's see number 54. That number 54 is actually that's a tricky question. I will call this problem effing tricky question. There's no way for us to integrate this. However, imagine if I multiply the top and the bottom by x. Multiply the top by x. I happen to see it though. So multiply the top by x and the bottom by x. Now then I get integral of x over x squared x to the 4th plus 1 dx. Then from here we use u sum. U equals to x squared. So du is 2x dx. Then our integral becomes 1/2 integral du over u squared plus 1. Do you see that?
Could you scroll up? Oh, wait, hold on. I gotta wait for this to disappear. Could you scroll up a little bit? Because I have this bar running across the bottom.
scroll up. Give me a second.
It's,
You mean?
yeah, this bar won't go away.
Oh, I see. You mean
Oh,
this way?
there it is. Now I can see it. Yeah, now I can
Uh-huh. Then from here, we do partial fraction decomposition. 1 over u times u squared plus 1 equals to 1 over a over u plus bx, I'm sorry, bu plus c over u squared plus 1. Multiply by the LCD. Give me 1 equals to a times u squared plus 1 plus bu squared plus cu. Apparently from here, when you look at the constant, on the left hand side is 1, on the right hand side is only a. When I look at the x term, on the left hand side is 0, on the right hand side, I'm sorry, not x term, u term. That's equals to c. While if we look at the u squared term, on the left hand side is 0, on the right hand side is a plus b. So the b is 1. It's 1/2 integral of 1 over u minus u over u squared plus 1 du. You can go on yourself from there. But the tricky part is actually trying to find a good substitution, and for that we multiply for the top and the bottom by x first. Now let's take a look on the next page, page 524. Let me know if you have questions. Let me ask you to pick 2 questions from there.
The questions for what page?
Page 524.
Okay.
Um, 74 maybe?
Okay, number 74. Any else? Oh, number 74 seems to be hard, but it's actually on the easy side. Happens to be on the easy side.
And 66.
Oh, if it's easy, then we don't have to do it.
No, let me show you. It's short anyway. Yeah. You know what? Sometimes some problems, it seems hard, but after you play with that a little bit, it turns out to be super easy. And I think this is one of them, because we can split them, right? This is 4 to the x over 2 to the x dx plus integral of n to the x over 2 to the x dx. Now the thing is, they have common exponent, but different base. So I can write it this way. So this is basically integral of 2 to the x dx plus integral of 5 to the x dx. Now I hope you remember how to do this. The derivative of a to the x respect to x is itself times ln of the base. Now, if I go backward, then this is,
I thought it was
It's-
1 over ln of
repeat it again.
5. Or isn't it over ln, like divided by ln of a?
Yeah, if we integrate.
Oh, right.
Yeah, if we integrate, that's right. Okay. Okay. That's for number 74, number 66. That happens to be something I see right away though. Number 66. Wish me luck. No, I guess no luck. Pi over 4 to pi over 3. And then natural log of tangent x. This is a parenthesis. Over sine x cosine x. Okay. Any plan?
Is this U substitution where we U sub ln tan x?
U sub ln. Okay, let's try. I don't know though. I don't know. So ln of tangent x. So the derivative will be 1 over tangent x times the derivative of tangent is secant tangent.
Secant squared x, I think.
Yeah.
Duh, what am I doing? Secant squared x dx. Let's see if we can simplify. Who knows we simplify something nice. So secant squared, that's cosine square at the bottom. Tangent means that's cosine and sine. Like this. Which becomes dx over sine x cosine x. Oh, okay. So if we use that kind of substitution, then we will get integral of u times du, huh? This u coming from here. That's my u. And then my du is dx over sine x cosine x. That's my du. Now, how about the limit of integration? When x equals to pi over 4, then I get ln of 1, right? That's 0. And ln of radical 3. So the limit of integration now becomes from 0 to ln of radical. I think you can go on yourself from there, right?
Could we possibly do number 82 or 80? One of those two.
Let's do both. Why not? But I don't know what's the question, so I cannot promise you anything. Number what?
Number 82.
Number 82. Integral of sine x cosine x big over sine to the 4x plus cosine to the 4x dx. Okay. You think, I think.
Isn't the denominator like an identity where it's like sine square plus cos square equals 1? So in a way it's sine square plus cos square to the power. Also squaring that, so wouldn't it be 1 to the square power, or
Maybe that's how we need to play that. So your issue is, I use red color so that I know what to erase if this is not correct. Honestly, I have no clue at all. I think what I will do, you know what? I think what I will do is I change everything into sine because I have extra cosine. You can change everything into cosine too, right? Okay, so let me change it this way. So this is sine to the 4th x plus, this is 1 minus sine squared x being squared. So this is 2 sine to the 4th x minus 2 sine squared x plus 1. Is it right? And if, let me update ourselves first then, this is equals to integral of sine x cosine x over 2 sine to the 4th x minus 2 sine squared x plus 1 dx. I think from here then I do a u sub, u equals to sine squared x. Or you can also say u equals to sine x, that will work. Don't worry about it. But the reason I say this because I see that the derivative is 2 sine x cosine x dx. Which means, now I can go here, that's equals to 1/2 integral du over 2u squared minus 2 plus 1. And then how to work on that.
If you separate it, then you can
What do you mean by separated?
like. Oh no, sorry, never mind.
What I think we can do is we complete the square root. Yeah, can do better than this. Yeah. Let me factor the 2 out first so that I have a better view. Don't forget, this is number 82, not supposed to be easy, right? So that would be u minus 1/2 squared plus 1/4. Okay, then from here we can do another user. Let's say W equals to U minus 1/2, so dW equals to D. I really wish, if possible, to skip that step.
Can't you just use the memorized integral of the tangent inverse?
Yeah, that's what I have
like
in mind.
one.
Uh-huh.
Oh,
Yeah, that's what I have in mind. So this is 1/4 times 1/1/2 tangent inverse of W over 1/2 plus constant. So going further, this is 1/2 tangent inverse of 2 times W. But what's my W? That's 2U minus 1C. And what's my U again? Sine squared. This is 1/2 tangent inverse 2 sine squared x minus 1 plus C. I'm not sure if we can simplify this first, desimplify this further though. I don't think so. I think it's the first I can go. Maybe one more problem?
Maybe
Oh.
69.
Number what?
69.
69. Number 69, we have integral from 1 to radical 3 for square root of 1 plus x squared over x squared dx. Anybody can suggest something? X equals what? I think I will use x equals to tangent tangent theta. So 1 plus x squared is secant squared theta, and square root of 1 plus x squared is secant theta. And dx is secant squared theta. D theta. Then this integral then becomes This will be pi over 4, and this is pi over 3. I believe. On the top, I get secant theta. X squared will be tangent squared theta. Then I get secant squared theta d theta. Any good plan?
Do we do the substitution? We have an extra secant theta, so I want to say it has to do something with tangents.
With tangent?
If I recall, yeah, I feel.
Let's see. So let u equals to tangent theta, you mean? So du is equals to secant squared theta, d theta. But I have issue with the leftover secant theta.
Yeah,
Is it easier to simplify first and then with secant equals 1 over cosine and tangent is or 1 over tangent squared is cosine squared over sine squared?
That's what I have in mind originally, but I'm not sure. I mean, some of you may have better idea. So sine squared theta, cosine squared theta. That's for the tangent square. And then the secant cube on the top becomes cosine cube at the bottom. So this becomes integral from pi over 4 to pi over 3. We get 1 over sine squared theta cosine theta d theta. Does it help? I guess not, huh? That would be cosecant thingy. Nah, I don't think I'm gonna go to that direction. Any plan? Maybe not. Maybe not like this. Let's see another way. Let's redo this problem. Number 69. Integral from 1 to radical 3 square root of 1 plus x squared over x squared dx. Now, I'm not saying that our approach above is wrong. We basically just get stuck. That's what I want to say. Yeah, we get stuck. I get stuck here. Changing it into sine cosine doesn't help, apparently. Let me play a little bit further from here. Who knows? It's doable.
Maybe splitting up the secant cubed into secant squared and secant?
Like what?
Or sorry, no, never mind. And then tangent squared theta plus 1.
This is sine squared theta cosine theta. I try to see that from cosecant cotangent point of view. I wonder if it is doable. It's cotangent squared theta. Cosecant cube. I wonder if it helps. No, I don't think so either.
Is there a way to change the secant squared theta to tan squared theta plus 1?
Oh, let's see. So this is integral from pi over 4 to pi over 3 of secant theta 1 plus tangent squared theta like this over tangent squared theta d theta. So the second term is nice, the first term is not really nice. Yeah, the first term I will get secant theta over tangent squared theta. Plus the second term is nice. It's just secant theta. I mean, integral secant theta is ugly, but at least it's doable. Right? But I have issue with the first part. If just for fun, if this is the reciprocal, that will be a lot easier, right? If we have tangent squared on the top and secant theta at the bottom, there's a regular U substitution, right? But it's not. Unfortunately, it's not. So I guess not. We get stuck. So the word stuck is actually a curse word also because it has the same the last three letters are the same with our curse word. Let's see. Imagine if, suppose I do it this way. So I use that u squared equals to 1 plus x squared. So basically u equals to square root of 1 plus x squared. So on the top, I will get, let me scroll it down. So I will get integral. On the top, there will be u. At the bottom, there will be u squared minus 1. And how about the dx? The dx 2u du equals to 2x dx. The 2 cancels, and x will be u squared minus 1. U, that's ugly. Not nice. Another way. Still ugly.
Did you do u is equal to tangent?
You mean x equals to tangent?
Yeah, tangent. And then dx is secant squared theta.
That's what I did.
That's what we did right there.
Unless you check if I make a mistake though.
I think if towards the bottom, if you do, so when we separated the integral of secant theta over tangent squared theta, I believe that simplifies to cosine theta over sine squared theta. And if you use sine squared theta as your u, then your du is 2 sine theta cosine theta. And then the cosines cancel out and you have 1/2 times 1 over u times radical u. And then
Let's see. So sine, cosine. So there'll be cosine theta here and sine squared theta. Oh, duh, this is so nice. Why I didn't see that? Is it like this?
yeah.
And then integral of secant theta is natural log of secant theta plus cotangent theta from pi over 4 to pi. Well, thank you. And this one we can go on already. just use u sub, right? U equals to sine theta, so the u equals to
I did sine squared theta.
sine squared theta for the u.
Yeah.
I don't think that's what you want to do.
Oh, right. Sorry.
Okay, this is better already. Well, you give me. I didn't see that coming though. I hope. No. Then I do that substitution. Then sine power over 4 is radical 2 over 2. This is radical 3 over 2. This is u to the power of negative 2 du. Dot, 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 dot. Okay, I'm about to stop right now. Let me give you the suggested homework. Basically, I would like you to do suggested homework from here. Is basically the odd numbers. From number 1 to number 81 maybe.
You said do all the odd ones?
Yeah, just do the odd ones.
Professor,
Uh-huh.
and then I don't know if you put it in discussion, but do you know what's going to happen with the syllabus at this point?
I will keep the test dates the same.
Mm-hmm.
I will keep the test dates the same. I think last time I said that we moved the test date, test 2 date to, let me write it down. Test 2 date moved to, anybody remember? Otherwise I need to get my test 2 was postponed to after, supposed to be after the spring break,
yeah.
right?
It was supposed to be April 1st.
Yeah.
And then we postponed it to be after spring break.
Mm-hmm.
And then on the 13th, that's they say that's the no class day. So then I think we move it to April 15th.
Yeah, I thought the quarantine was extended too until the end of April now as well.
That's right. That's why then everything goes online.
Mm-hmm. Well, I mean, so how far into the book are we going to get at this point? Because it seems like aren't we pretty far behind?
We are 1 week behind.
Only 1 week? Okay.
Yeah, we are 1 week behind. Once we are done with this technique of integration, the ones from chapter 8 is actually not too much.
Okay.
Okay, and then we skip chapter 9.
Mm-hmm.
And then we go 10.1, 10.2. And chapter 11, we basically need to cover all. Now, here's the thing though. Even though it seems like we are 1 week behind, at the same time, then you have more freedom to do a lot of watching online lecture video, which I plan to do starting from maybe today. So after today, I will get the recording from the state on these lectures. I will post it on YouTube, and then I will also post it on our discussion again on the discussion board we have today. And then I will have another announcement for you to study for the next on this Wednesday. Now, in that announcement, I will give you the link to lecture videos, so you can watch it at home at the time of your leisure, basically. Now, that watching lecture video at home will speed up our class actually. So you will see that the structure of our class basically changed from lecture in class and you do problems at home to be right now. The lecture is done basically online. You watch it during your whatever, not off class time. And then during the class time, we do question and answer.
Okay, that makes sense.
Okay, yeah. Another thing, do you guys know what will happen on your tests? How do we do our tests later on?
No.
No.
No idea? Okay, basically it will be as the following. I will post the test online and then you print it out.
Okay.
After you print it out, you work it out on that paper and then you take the picture.
Hmm.
Now, after you take the picture, you will convert that to PDF. Then you upload that to Canvas.
Is it fine if we scan it?
Oh yeah. If you have scanner, that's even better. I have students saying that what happens if they don't have scanner. If you have scanner,
Okay.
that would be the best.
I think
Okay,
everyone has a scanner on their phone.
that's what I have in mind. You can take the picture, and then there's something called Cam Scanner that can change your picture into PDF.
Is there a timeline for how long we have to do that?
I basically give you the whole period plus 15 minutes for you to upload them.
Okay.
Yeah.
And
Okay.
what sections are gonna be on it?
I don't know yet, to be honest with you, but we know for sure it will be from after your test 1 up to approximately somewhere in chapter 8.
Okay.
Yeah. Okay.
Oh,
Now,
yeah.
but here's the problem though. Then I have some students asking me, Thomas, what happened if I don't have printer? Any of you don't have printer?
Me.
Okay. But do you use Surface or iPad?
Yes.
Now, then you can just upload that test on your pad and then work it out directly from there.
Okay. Or can can I take a picture?
Okay.
No, that doesn't make sense. Okay.
What do you mean by take a picture?
Or can they use a blank sheet of paper and just send you like the
Yes,
work?
you can write it down and then work it on that paper and then send it to me. Okay, that's actually the worst way. Okay, but it's still doable that way. You know, I gave a test last week with my Santa Monica students, and one student brought up the issue that Thomas, I'm actually using iPad. Can I just upload that to my iPad, work on that right away, and then just send it to you back? And that's actually the best one. So no paper need to be involved. You see what I mean? But the big picture is like you print it out, you work on that, and then you scan it back to me on Canvas. Now, if you have more efficient way than that, go for it.
Will you post the exam like a few minutes before so we have like a chance to print it?
Actually, what I have in mind, I will post it like half an hour before the test.
Oh, okay.
Okay, that's good.
You know, that's to help students who don't have a printer. But then somebody actually brought this issue to me. You know, Santa Monica students. There's one of them. I'm sorry to say that he was just a complainer. He said that Thomas, it's not fair for those students who don't have printer. If I don't have printer, then I will take more time to write it down and less time to do the problem.
Mm-hmm.
Do you know what I say to him?
No. What'd you say?
Get a printer. No. Here's the thing though. Here's the thing. Because somebody don't have printer, okay, I already have in mind, if you don't have printer, then I give extra time, right? But when I give extra time, I cannot give extra time to those who have printer only, as if I penalize those who has printer. You see what I mean?
I see what you're saying.
Right? If students have printer, then they're supposed to have the benefit of having printer, right? If I give extra time to those students who don't have printer, I cannot take that time away from those who has printer. As if I'm penalizing them. You know what? You have something more advanced, and therefore you have less time. I cannot do that.
Yeah.
Right?
So everyone just gets 30 minutes extra.
Yeah, 30 minutes extra and 30 minutes extra before the test, the class start, and 15 minutes extra to upload it to Canvas. Now, the thing is you need to know how to upload it to Canvas fast. The reason I asked you to make it into PDF is because when you upload JPEG, it tends to take a lot longer time. You know, that's why I change it to PDF first and then you upload it.
Okay.
Okay?
Mhm.
Let's meet on Wednesday. Between today and Wednesday, I think I will post some lecture video from YouTube for you to watch. The next material we will do is 7.8. I may show you the lecture video for 7.6, the approximating integral, but that will not be in your test. It's just to show you how we actually do it in practice if we cannot integrate. Okay, then see you then on Wednesday.
Okay,
One
thank you.
question. Do you
Oh,
have
yes,
office hours?
My office hour basically the same to the syllabus from 3 to 4:25.
They'll just be in the Zoom conference before, right?
Yes, so that's what I did earlier when nobody was in class. So when nobody was in class, then I actually you do this 7.5 example A and 7.5 example B instead of me sitting here doing nothing, right? So that's what I did. But my office hour basically the same with the syllabus. I tried my best to keep my syllabus as is, you know. It's just the method then suddenly becomes remote.
Okay.
Okay? Okay, see you then on Wednesday. My office hours start at 3 o'clock, maybe a bit after.
Okay, then see you then, Professor. Take care.
You too? Hey, stay covidly negative.
I'll try my best.
Okay, bye-bye.
Bye, Professor.
Bye.